it's just Ben and I. We're going to go over our previous work, and then we're going to cover Root-locus. I should say week 10. All right. So we've already shown you all this before, so I'll kind of just go through this really quickly. But we're interested in, for the constant input, we're looking for constant input, step responses, and frequency response constants. This is what our system looks like. Again, the heater is located here, and the sensor is located next to it. We have a blower blowing across the sensor, cooling it off, cooling off the heater, and we read that. We pick up that data, record it. You've seen that before. That's what our system looks like. Again, that's our operating ranges. That's what our steady state looks like. Again, we didn't, because we were limited in the amount of time that we're able to record the data, what we considered the steady state is actually just the last about 40 seconds of the experiment. We thought that would be most appropriate data to use for a steady state. So go through this. There's our SSOC again, through the various output ranges that we were interested in. If you'll notice, all three have a negative gain. Something interesting happens towards the bottom here. We have a little bit less steep of a slope on our gain there. I'm not sure why, but it's just something that happens. And that's all of our data for the constant input with the outputs. Step up and step down modeling. There's an example of a step down. There's a step up. There's a step up again. That's our limitations we were trying to show you there. The transfer function. So we found the constants there. I apologize. Hang on. There's our constants again for the step up, step down data. Those are our conclusions. Frequency response. Okay. That showed up there, didn't it? That was pretty fun. Okay, so now we're on the frequency response data, and we're interested in the variables for our frequency response, which should be coming up. Okay, here's our Bodie plot that we put together after we got all of our data. With this should be the phase angle, and that should be the amplitude ratio. We were using the graphical fit method in order to find our order, which was 2, our KCU value, which that's the inverse of it, our gain, which is the asymptotic value here, which is 0.19 degrees Celsius, and the ultimate frequency, which was 0.08 hertz. The amplitude ratio's equation is there, as well as the phase shift equation. That was our result. These are our results for the Bodie plot, given doing it graphically, as you saw there, just using the Bodie plots. All right, here's the fit method. This is new to our slide. This is new to our presentation here. We used the model that was presented to us online to fit the data points. Here were the values that we got for our gain, our controller gain, our ultimate controller gain, I'm sorry, tau, our time constant, and our dead time. There are the model equations that were used. You can see it fits pretty nicely, so we were happy with it. Here's a comparison of our constants across the model and across the visual Bodie plot. You can see they all kind of changed a little bit. You expect that as you can get more accurate with the model equation in Excel. Here's the root-locus theory. The roots of the first order plus dead time, the open loop equation are listed here. Zeta is the damping ratio. The decay ratio is listed there. What they consider the decay ratio. We're interested in underdamped, or I'm sorry, maybe it's overdamped. Stable. We're interested in creating a stable system, so we're interested in all of these which are labeled stable and oscillatory. So this is our open loop diagram here, and for a proportional controller, you just insert a controller gain between the input and the transfer function for the FOPDT, which is listed here. And we all know that when you multiply these together, you get the open loop transfer function, which is listed here, which you can see that we could find different variables of KC, different values for KC that will affect our overall system's performance. This is the effective damping ratio on the second order underdamped step response. You can see here that as you change zeta, you get a faster, I think it's an overshoot, or time, you get a higher value here, and it decreases with various zetas between 0 and 1. This is our Root-locus plot, and you can see where the zetas vary according to the KC values. This is 1/10 decay occurs here, 1/500th decay occurs here, and this is the KC value for 1/500th decay, 1/10th decay, quarter decay. This is the ultimate controller gain, where zeta is 0. This is everything left of the real axis is sustainable. They won't go crazy on you. And here are our results. These are the KC values we obtained using those various zeta values that were assigned to us.